Okay, welcome back to AI for Mechanical Engineering, and we're going to learn about singular value decomposition. Before going into singular value decomposition, let's also think about the meanings of linear maps. So when we're talking about a matrix A, this is a linear transformation, and this is actually rotating and stretching or compressing a vector in one domain to another. So for example, if we have these vectors v1 and v2 in the domain of A here, and if we multiply A to our vectors, so we have AX, something like here, so this v1 can become sigma 1 u1, and v2 will become sigma 2 u2 if we multiply our matrix A here. And an extremely important fact here is that every matrix A, which has the size of m by n, maps a unit ball in Rn to an ellipsoid in Rm, as we saw before. So here, for example, if we are multiplying A matrix, which has the size of m by n, and v1, which is a unit vector in Rn, so it has the size of n by 1. This will be sigma 1 u1, where sigma is a scalar and u1 is a vector of m by 1. So this becomes an ellipsoid in Rm. So here, this v1 is our unit ball. And what happens here is we're going to have some rotated plus stretched or compressed vector, so it becomes some ellipsoid in Rm. So when we're doing singular value decompositions, these are talking about singular values and singular vectors. And the numbers, sigma 1 to sigma n, these are called as singular values of A. And by convention, sigma I is larger than 0. And however, these words of singular values and singular vectors, these are something similar to eigenvalues and eigenvectors. However, when we're calculating eigenvalues and vectors, we had squared matrix, A which has the size of like n by n, the same row and same columns. However, in singular value decomposition, we're calculating something from an A matrix that is not a square, m by n. So the singular values of A matrix is something similar to the eigenvalues. And the singular vectors in our A matrix is something like our eigenvectors. And here, we're going to have two different vectors, u1, u2 to un. These are the unit vectors along the principal semi-axis of AS. And v1 to vn are the primitives of the principal semi-axis, defined so that we have this AVI equals to sigma I UI. So here, VI, this has the size of n times n by 1, and UI, this has the size of m by 1, because our A matrix is in the domain of n by n. So what we are doing here is actually, we are having some column vectors of V here, and you can think this as the unit ball here, V1, V2 to VR, and we are multiplying this with A, and then this finally leads to sigma 1 U1, sigma 2 U2, sigma RUR, and we also can simplify this notation using this expression as U column vectors multiplied with sigmas, where these are singular values, and this is a diagonal matrix. So we have this equation here, that AV, the V is the matrix with our unit vectors of V1 to Vn, and U, this is V1 to VR, sorry, and U is the matrix which has the unit vectors of U1 to UR here. And sigma, this is the matrix that includes our singular values in our diagonal terms here. So now let's talk about singular value decomposition, especially with a thin matrix. Let's say that A is a skinny and full rank matrix, where skinny means M is larger than N. So we have a skinny matrix here. And let's say that this is full rank, so R equals to N. So here, then we know that AVI equals to sigma IUI for I from 1 to N. And of course, I'll just write this again, that A is the size of M by N. N has the size of N times 1. Sigma I is a scalar, and UI is a vector with the size of M by 1 for I between 1 and N. So what we're going to do here is we're going to try to decompose our A matrix into these matrices here, U, sigma, and V here, because we know that AVI equals to sigma I UI. And this U matrix are filled with orthogonal unit vectors. And this sigma, these are all our singular values. And V, this is also orthogonal unit vectors. So what we know here is we're trying to decompose our A matrix, which has the size of M by N, using our U matrix here, which has N unit vectors, and the dimension of each unit vector is M. Here you can see that the size of our UI is M by 1. So that's why we have M and N here. And this sigma is our diagonal matrix with the eigenvalues of N. So R equals to N, this is full rank. So we have N eigenvalues in the diagonal term here. And this V transpose has the size of also N by N, which is also the unit vectors, orthonormal unit vectors, where VI, Vj, if we do these inner product between two unit vectors in V, these will be 1 or 0. So 1 if I equals to j, and 0 otherwise. So that actually leads to this fact, that V transpose times V equals to identity matrix here. So therefore, if we use this fact into this equation that we actually saw in the previous slide, AV equals to U sigma. And if we multiply V transpose in both the left-hand side and the right-hand side equation, we get this equation here, because V transpose times V is identity matrix. So therefore, we can decompose our A matrix with the size of M by N using some matrix filled with unit vectors of U, some matrix transpose filled with unit vectors of V, and some diagonal matrix that is filled with singular values. So we're going to talk about the details of how we can get these unit vectors U and V and the singular values a little bit more later. So before doing that one, let's also talk about doing full singular value decomposition, which actually we're not going to do this very much in practice, because usually we are doing singular value decomposition with a thin matrix. So if you want to do full singular value decomposition, you can just simply add some extra orthonormal columns to U. So here, this was actually 0. There was nothing here in the previous slide. However, you can add extra orthonormal columns to U and add extra rows of zeros to sigma. So these are our singular values as the diagonal terms. And you can just add zeros in the bottom here. So actually then this becomes meaningless. Then you can also do some full singular value decomposition, but however, we're not going to do this in detail because thin singular value decomposition will be used in practice much more frequently. Let's also interpret singular value decomposition. So when we're doing singular value decomposition, we are doing this decomposition of matrix A into U, sigma, and V transpose. And for example, let's think that we're doing some multiplication of a vector x to our matrix A. Then what we can first think here is we're first doing some rotation by V transpose. This V transpose, actually, these are filled with unit vectors. So V transpose V is an identity matrix, and every VI transpose VI will just be simply 1 or 0. So that means that this will not affect the magnitude. So it will only do some rotation. So we first do some rotation by V transpose, and then here, we multiply this with the matrix that is filled with our singular values, and this indicates that we are doing some diagonal scaling by our singular values. At the last, we are also doing some rotation by U here. And here, U also, these are unit vectors, and these will not affect the scaling. So these are also only rotation. So this is how you can interpret what is happening when we are multiplying some matrix A to one vector. So we are transforming some unit ball X to some ellipsoid in some other domain when we're multiplying a matrix A. So one thing that we need to note here is when we're multiplying X here, it's unlike eigendecomposition. In eigendecomposition, what we did is we're doing something like AVI equals to lambda VI, lambda I VI, and the size of these two matrices were the same. However, in singular value decomposition, we're doing something like this one. AVI equals to sigma I UI, and the size of VI and UI are different. They have different dimensions. So that's also one thing to note when we're doing singular value decomposition. So for any matrix, arbitrary matrix with the size of m by n, we can do singular value decomposition, and A will be decomposed with matrix of U, sigma, and V transpose. However, for a special case where we have a symmetric and positive definite matrix A, which you can think that this is m equals to n. So we have a square matrix, like an n by n matrix. So A can be seen as S times lambda times S inverse, which equals to S times lambda, and S transpose, where S is our eigenvectors. So this is a special case of SVD. Okay, so for singular value decomposition, the most important problem is to find our U and V unit vectors. How can we find those? And then what's going to be our sigma here? If we find those vectors, then it means that we can successfully do this decomposition. And let's talk about an A matrix, which is skinny and full rank. Then we can construct two positive definite symmetric matrices, A transpose, and A transpose A. So if we do A transpose, you can think that we're creating a matrix that has the size of m by m. And if we calculate A transpose A, you can think that we are creating a matrix that has the size of n by n. So then these matrices becomes positive definite symmetric matrices, A transpose, and A transpose A. So therefore, it means that we can do some eigendecomposition on A transpose, and A transpose A. So for example here, we can see that A transpose equals to U sigma V transpose times V sigma transpose U transpose. And we calculate this, we get U transpose and some multiplication of the diagonal matrix in the middle. And for A transpose A, similarly, we have V times something in the middle and V transpose here. So what you can see here is when we're doing eigen decomposition, when we have a real symmetric and positive definite matrix, then this S was a matrix that contains our eigenvectors. Therefore, if we do eigen decomposition of A transpose, this one will be our eigenvectors of A transpose. Similarly, V and V transpose, these will be eigenvectors of A transpose A. And we're going to have n by n and n by n for A transpose A and A transpose. And we're going to have n eigenvalues and n minus n zeros here. And we're going to have the eigenvectors in U. We're going to have n eigenvalues and V eigenvectors here. So that's how we can find our U and V inside our, when we're doing our singular value decomposition. Now let's also take a look into the relationship between PCA and SVD. So let's think about, we have this B matrix, which is actually A transpose A. And we know that we can do some eigen decomposition because here now this A transpose A, B is a square matrix. And then we can decompose this into V times lambda times V transpose. And this actually, what you can see here is this A transpose A. If A was our data, if you imagine that A was X, then this is calculating our covariance matrix. Because covariance matrix was 1 over M X transpose X. And you can think that, you can just simply substitute A into X here, and you can know that, okay, this is simply our covariance matrix. Therefore, we can simply find the eigenvectors of the covariance matrix we calculated here. That means the columns of V are the principal axis. So therefore, when we're doing SVD, and especially when we're calculating A transpose A, and when we're finding the eigenvectors here, so in the V matrix, these V matrix actually are the principal axis. So we can also find the principal axis by using singular value decomposition. So finally, now let's also talk about dimension reduction using singular value decomposition. So firstly, let's imagine that we have some vector x. And let's say that we are doing some linear transformation using our matrix A. And if we write this, we're going to get some equation like this one. U1 sigma V1 transpose X plus U2 sigma 2 V2 transpose X. And if we write this in a matrix equation form, we're going to get some equation like this one. Here we have our U1 vector, U2 vector, V1 vector transpose, and our singular values, sigma 1 and sigma 2 here, and with multiplied by x here. So actually, this is U times sigma times V transpose times x. And we know that this is sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose x, because actually sigmas are scalar values, so we can put sigma in the front of these multiplication of the unit vectors here. So in general, in more general cases, we're going to be able to express our singular value decomposition A, which equals to sigma R VR transpose, into the sum of sigma I UI VI transpose from I equals to 1 to R, where R equals to N if it's a full rank. Now, this is important. So if we're trying to do dimension reduction, it means that we're trying to select some dimension that is smaller than R. Then the only thing that we need to do is we can reconstruct A using only K information of our singular value and our singular vectors. So to draw this in a more graphical way, we know that our A matrix has the size of M by R, and we're decomposing this to U, sigma, and V transpose. And here our U, this is M by R, sigma, this is R by R, and also V transpose, this is also R by R. And when we're doing singular value decomposition, we obtain these matrices, and we can do dimension reduction by selecting the highest singular values inside our sigma matrix here. If we only select these ones, it means that we're only just using these information. Let's say that we're using only K amount of eigenvectors of the inside the U matrix. So this sigma matrix is also K by K, this small one, and this V transpose also. We're going to have something like here. We're going to select K here. So we have a K by R matrix here. So now we have a matrix multiplication of M by K, K by K times K by R, and the final result will have the size of M by R, which is the same with the original matrix A. So even with a part of the eigenvectors in U and V, we are able to calculate, we are able to also reconstruct our A matrix using a smaller information. So one example for this one is actually here. So here, this was actually a two-dimensional example. We had sigma 1 and sigma 2 as our singular value. And let's suppose if sigma 1 is much larger than sigma 2. For example, like sigma 1 was 100 and sigma 2 was 0.1. Then what we can think is, we can think that this effect from this singular value, sigma 2, will be very small to our decomposition of A. So we're going to be able to approximate or reconstruct our A matrix using a single unit vector U1 and V1 transpose with a singular value sigma 1. So that's how we can do singular value decomposition to do some dimension reduction. By using SVD, singular value decomposition, we can do very interesting things. For example, we can reconstruct image using less information. For example, if we have this image here, A, original image here, and if we do singular value decomposition, SVD, and extract information of the singular vectors and singular values as these ones, if we only select the most significant singular values from the top, for example, here we select the top 20 singular values and their corresponding singular vectors, and we reconstructed our image like using these 20 singular vectors here. So what we can do here is we can actually get a very large save in memory. For example, let's say that this had a matrix size of 1000 times, let's say arbitrarily like 1000. Then it means that we're going to be able to represent this 1000 times 1000 image using the information of 1000 times 20 as our U vector, or as our U matrix, and 20 times 20 as our sigma matrix, and V as 20 times 1000, which is actually a much smaller memory that is required compared to the memory for the full image size of 1000 times 1000. Also, we can do some very interesting example that's called eigenface, which is we are extracting the important modes included the faces in the US presidents. Let's say that we have 12 faces here, and each face contains the pixel size of 250 times 200 here. So what we do here is we form a matrix A with all of the faces. However, when we're doing this, we're going to vectorize each face. So here, for example, this 250 times 200 face comes inside here. So we have a long column with the size of 250 times 200. Face 1, face 2, until we have face 12. So then it means that we are having a very large A matrix, which actually has the size of 250 times 200 times 12. And we're going to decompose this using singular value decomposition using U, sigma, and V transpose, where our U matrix will have the size of 250 times 200 times 12, sigma 12 by 12, and V transpose as also 12 by 12. So if we multiply these ones, we're going to have the size of 250 times 12 here. And based on this A matrix, we're going to do the mode extraction. I'm going to call this as the eigenmode extraction. And therefore, this 12 faces, these are actually the columns of U. U columns UI. So each column has 250 times 200 size vector, and we reshape this into a face. So these 12 modes are the most important modes that can represent the faces of all of our 12 US presidents here. So we can also do these kind of mode extraction using singular value decomposition. The last example that I would like to introduce is seeing through a disguise with singular value decomposition. We have this 250 times 200 sized image here. And what we're going to do is we're going to project our image with some disguise of this sunglasses onto our mode U. This is our mode, the eigenmode, learned without disguise. So if we do this projection on U, this becomes U transpose times X. Let's say that this is the image X, and this U transpose, we have the size of 12 times 250 times 200, and our X has the size of 250 times 200 times 1, and therefore this becomes 12 by 1. So if we project our image here to our eigenmode here, we're going to get a vector with size 12. And these are actually the coefficients that corresponds to each eigenmode, the eigenfaces. So let's say that these are lambda 1, lambda 2 to lambda 12. And based on these coefficients, we can also do some reconstruction from here. When we're doing reconstruction, we can do this by x prime equals to U times U transpose X. And here, U, of course, this is the size of 250 times 200. So U has the size of 250 by 200 times 12. And U transpose X has the size of 12 by 1. So if we multiply these two, we're going to have 250 times 200 sized vector, which we can reshape this to a image here. And the meaning of this one is actually we're doing some reconstruction, I equals to 1 to 12 from lambda I and ui, where this lambda I was solved here. And therefore, this lambda I will be the highest for the most similar photo, and we are able to reconstruct our face even with a disguise here, because we can we are able to find the combination of lambda I that will generate the face of this president here. So these were some examples of using singular value decomposition, and I will do some demonstration of SVD using Python and Colab. So let's take a look into doing the example of SVD for image approximation. So firstly, to do this, you'll need to download an image here, or you can use any different kind of image. So inside this link, you're going to be able to download an image, and if you want, you can locate this into your Google Drive, or simply for just as this is a toy problem, I'll just upload this into my Google Colab directory here. If you just click this files here and just copy and paste. For example, this image file was postec.jpg. If you locate postec.jpg here, and then you can just simply import this using CV2 library here. So just read your image here. Then you can see that this image is red, and we have the image size of 642 by 642. And I'm going to, this is a plot of this image. So if you run this, you're going to see this image here of postec. And we're going to do singular value decomposition of this image of postec. So I'm going to define our image using our variable a, large A, and I'm just going to simply use the SVD function provided from NumPy, numpy.linearalgebra SVD, and then you're going to get our U matrix, our sigma matrix, which is filled with our singular values, and our V transpose matrix. So here we can calculate and get all of the informations, and if you print this, you're going to get some information like these ones. So the important thing here is actually, let's first look into the shape of these matrices. So U 642, 642, and the singular value is also 642, 642, and V transpose also 642, 642, because this is a square matrix. Now we're going to try to approximate this image using only a part of our singular values, not the whole of the 642, but for example, using 20 singular values. So now we're going to extract the U matrix that is relevant for these 20 singular values here, low U, and also extract the sigma values, the singular values that is relevant to k equals 20, and also for V transpose. And then if we multiply these matrices, U times S times V transpose, with the part of the matrices which is relevant to k equals to 20, we are now going to be able to also approximate our image. This is not fully approximated. However, we can also approximately see that this is an image of postec. So it is quite nice to see this, because we can have a less memory for saving this image when we use singular value decomposition. Also, similarly, for example, you can change the number of your singular values from 1 to 600, and then you're going to see that the approximation improves when we increase the number of singular values for reconstructing our image. So for 600, this is almost near to the original image, and also 30 is quite really nice. The next example that I explained in our slides were these eigenfaces. You can also download the face file from this link here. Just click this, then this will redirect you to the download. And we can also do this. Eigenmode decomposition by first loading our face data. So our face data is actually this faces.mat, and you can also just locate your face data inside your local directory inside Google Colab here. And then if you just open this using SciPy IO library, then it will succeed to open your faces.mat file. And then what we're going to do is we're going to plot our faces inside our data. You can see the 12 president faces. And what we're going to do here is we're going to reshape our face data into the shape that we talked in our lecture parts, in our slides. So here I'm going to reshape this with row times column. So 250 times 200 and m. This is probably the number of the faces that we have inside data. So then, if we prepared our A matrix, we're going to do SVD, also using NumPy's library, and then it's finished. We have done SVD, and the eigenmodes inside of the eigenmodes can be extracted from the eigenvectors of our U matrix, and we can plot the eigenmodes. So here, I'm plotting the eigenmodes here, U and ith column, and if we plot this, you're going to see some plot like this one. You can just simply run it by clicking this button. And then these are the 12 eigenmodes that can be used to reconstruct the faces of the US presidents. And we can also calculate the singular values and see how the magnitudes of the singular values decreases. So we have singular values 0, 1, 2, and we can see pretty much that this first two or three, the first two singular values are pretty much significant in our SVD, the decomposition. So let's also talk about this example of seeing through a disguise using singular value decomposition. And you can also download this image file that has the disguise of this John F. Kennedy's image here with some sunglass. So download this image and just locate this also inside your local directory in Colab, and then just read it using CV2 library. Then you're going to be able to see this image. And what we're going to do is, as I told you before in the slides, we're going to first project this image with the disguise onto our onto our eigen faces. And this can be done with here. Oh, oops, actually a row is not defined here. And actually, this is because I didn't actually run the rows here. So I'll just run this again here. Row, column, and M. And let's see if it works correctly now. Oh, we don't have U also because I didn't run U. So let's also run everything here. Run the SVD. Then we get U. I'll also just run these ones, eigenfaces, singular values. And then, if we do this projection onto U, now it works because now we have all of the information required to do this projection. We did our projection of this image with the disguise onto U here by U transpose times X. And then we have done our reconstruction by multiplying U with the eigenface decomposition here. So then this means that we're going to reconstruct the image of John F. Kennedy using our eigenmodes that was extracted from the singular value decomposition without the disguise. So therefore, if we do this one, this is doing the reconstruction back to our eigenmodes, and therefore we are going to see an image of John F. Kennedy without the disguise. So that was some examples of using SVD for various applications.